Hello, and welcome once again from Cambridge, UK. I am Professor Sir John Aston, the Pro-Vice-Chancellor for Research at the University of Cambridge. I'm delighted to be giving the opening remarks for the second seminar in this important collaboration between Cambridge NeuroWorks and the PolyU Academy for Interdisciplinary Research in Hong Kong. I hope you enjoyed the first seminar with Professor Eddie Chang. His fascinating device that enables patients who have lost the power of speech to talk again just by thinking is an inspiration to us all. We also heard about the work of talented young researchers from both Cambridge NeuroWorks and the PolyU Academy. If you missed it, you can watch it again on YouTube. Today's talk by Professor John ROGERS promises to be equally inspiring. John is leading the world in developing humane and clinically practical neurotechnology. Neurotechnology has the potential to tackle some of the most significant health and economic problems facing the world. Depression, dementia, stroke, chronic pain, Parkinson's disease, incontinence, OCD. The world needs affordable, universally available solutions to these ills. But that won't happen unless we create a space where the brightest people with the boldest ideas are free to take risks, experiment, fail, learn from that failure, access real patients and their doctors, and then get business support to help create companies to manufacture their innovations at scale. That is the purpose behind our Cambridge NeuroWorks program. It is co-run by 9 partner organizations across the city, including Cambridge University, and it brings together experts in engineering, neuroscience, regulation, AI and data, clinical trials, and business, all there to support groups of funded fellows who've come to us from around the world to turn their bold neurotech ideas into reality. You're about to hear from 2 more Cambridge NeuroWorks fellows, Ali and Sam. Ali started her career in the liberal arts, then became a yoga teacher. And it was while teaching yoga to brilliant Cambridge scientist Tamar Machin, who runs the university's plasticity lab, that Ali became interested in neuroscience. She joined Tamar's lab 3.5 years ago to study for a PhD, and is now developing a device that helps to treat urinary incontinence. It's a non-invasive device that can help assess and then restore strength to the pelvic floor muscles, which are very hard to treat because they are buried inside you and you can't feel them. Sam was a Cambridge NeuroWorks fellow last year and now has spun out his own business called MALLIARAS, which is in the process of raising money. He is developing a device that offers remote therapy for people recovering from a stroke. Sam was inspired to design the device after his very young cousin suffered a stroke, and he witnessed how difficult it was to access regular therapy. His device enables physiotherapists to treat patients over the internet. We are excited about partnering with PAIR for these 3 online seminars. PAIR's focus on addressing major societal challenges, on global collaboration, and on partnering with academia, business, industry, and governments feels like the perfect match for Cambridge NeuroWorks. Today is about sharing ideas and creating long-term partnerships and friendships across the world, about creating a global community determined to improve the lives of billions of people. We encourage you to ask questions in the panel discussion, and afterwards to get in touch with us through the PolyU Academy or here in Cambridge through the Cambridge NeuroWorks website. Once again, welcome and enjoy.
Ladies and gentlemen, good evening, good morning, and good afternoon. It is my great pleasure to welcome you to today's Cambridge NeuroWorks and PolyU PAIR joint seminar. This seminar marks an exciting collaboration between Cambridge NeuroWorks and the PolyU Academy for Interdisciplinary Research, or PAIR in short, in the rapidly advancing field of neurotechnology. Through this platform, we hope to bring together leading researchers from around the world to exchange ideas, showcase cutting-edge research, and build new partnerships. By connecting researchers from PolyU and Cambridge NeuroWorks with shared interests and complementary expertise, we hope to inspire deeper collaborations in the years ahead. At PolyU, interdisciplinary research is at the heart of what we do. Through PAIR, we bring together expertise from diverse fields to address major global challenges. Under the theme of good health and well-being, PAIR supports researchers in areas such as future food, sports science and technology, smart aging, Chinese medicine innovation, mental health, vision health, and tourism. We believe neurotechnology and bioelectronics have an important role to play across many of these fields. From supporting the early detection of dementia and improving personalized care through AI and biosensors, to advancing our understanding of how novel treatments work, addressing these challenges depends on close collaboration across disciplines. Today, we are privileged to learn from the expertise of bioelectronic pioneer, Professor John ROGERS. In fact, the PolyU community had the pleasure to learn from ROGERS when he visited the university last year to deliver a distinguished lecture and workshop. We are delighted to welcome him back and to benefit once again from his insights. Adding to today's exciting program, we will also hear from two outstanding peer researchers, Professor Lianghua Lou and Professor Vivian Wei, whose work highlights the transformative potential of AI and digital technologies in advancing healthcare and improving quality of life. I'm very much looking forward to learning from their insights as well as from our friends at Cambridge NeuroWorks. This seminar series is about building a community of researchers who share a common goal, improving lives through science, technology, and innovation. I encourage all of you to participate actively, ask questions, exchange ideas, and continue the conversation beyond today's event. Finally, thank you for joining us. I wish you an engaging and inspiring seminar. Thank you.
Distinguished guests, colleagues, and friends, it's really my great pleasure to introduce today to the seminar speaker, Professor John ROGERS from Northwestern University in the United States. Professor ROGERS is an internationally recognized pioneer in the field of bioelectronics. At Northwestern University, he is a Louis Stimson and Kimberly Curry Professor of Materials Science and Engineering, Biomedical Engineering, and Neurological Surgery, with the courtesy appointment in electrical and computer engineering, mechanical engineering, chemistry, and technology. Professor ROGERS also directs the Curry Simpson Institute of Bioelectronics. Under his leadership, the Institute has pioneered breakthrough technologies ranging from soft, again-like electronics, to injectable and solvable devices. Many of those innovations have been published in leading journals like Science and Nature. Professor ROGERS' achievements have earned his numerous awards and honors. Due to limited time, I'm not going to list all of them. However, I'd like just to mention he is one of less than 2,000 scientists who earned the titles of fellows from all the three major U.S. national academies. That's the National Academy of Engineering, National Academy of Science, and National Academy of Medicine. And he's also a fellow of the UK's Royal Society. So without further ado, ladies and gentlemen, please join me in welcoming Professor John ROGERS.
Great. Thank you for that introduction. That was very kind. And I want to thank you and Professor MALLIARAS for the invitation to participate in this webinar. As was mentioned, I was there at PolyU about a year ago, February 2025, and I think the main focus of our discussions at that time were around scientific collaboration, and I think I gave a joint presentation with my longtime collaborator, Professor Yonggang Huang, so it was really interesting set of interactions and discussions. And then I think I gave a talk on technologies mainly designed for use with human subjects, where we have some pretty good momentum around translation. So, devices that have now been commercialized. This time I'll talk about something a little bit different, really focused on neural interfaces. And I have a tough act to follow in Eddie Chang. I have great respect. He's a tremendous pioneer in neuroscience and clinical care and technology development as well. But hopefully the content in my presentation will kind of complement his. So I'm not going to be in direct competition with him, I think, fortunately. I'm an engineer, and so we're interested in developing new technologies that can be used as tools for studying basic questions in neuroscience. Using animal models or organoids, ultimately with potential for use with human subjects, but with this near-term opportunity for us to kind of contribute to the broader neuroscience community through engineering innovation. And that's what I'll share with you in the next 30 minutes. The title of the talk is, kind of shown here. It's Bioelectronic Systems as Neural Interfaces. We've been active in this area almost 20 years now. And so there's a little bit of a historical perspective that I'll share with you sort of towards the beginning of the presentation, outline what we see as the opportunities in engineering and material science to advance neural interface technologies. I'll give a little bit of background where we started, which was in the formation of sort of electrical or electronic interfaces in the form of sheets and meshes for measuring electrocorticography, so microscale capabilities in that domain with very high spatial and temporal resolution. But most of the presentation will be focused on these last two areas where we still have, significant active efforts, and specifically thinking about not just electronic interfaces, but optoelectronic ones, exploiting various kinds of genetically encoded fluorescent markers and optogenetic modifications to allow for manipulation and monitoring of neural activity in the optical domain, and describe what we're doing in that space, filaments and sheets as well. And then in the last part of the talk, I'll describe some work that we've done in the development of three-dimensional neural interfaces, specifically organized around the study of cortical and spinal organoids and assembloids made with them. And so, as I mentioned, my background is in engineering, and that's where we think we have our main areas of uniqueness, building on novel materials into engineering systems, but it's all very interdisciplinary, kind of in the pair spirit, I guess, in terms of the orientation of the research. So let me begin with the opportunities. So this is an invited review article that we published a few years back in the journal Cell, and it's really just to outline where we think there are some frontier opportunities for academic research, building on the broad range of FDA-approved neural interface devices that are currently used with great effectiveness in treating symptoms of Parkinson's disease, for example, retinal and cochlear implants to restore vision and hearing, stimulators that interface with the vagus nerve, spinal, peripheral nerves, and so on. And I think those are great technologies, but they're starting points for a range of engineering enhancements that we think will expand the range of application, ultimately for human subjects and treating patient conditions. But as I mentioned before, in the near term, the development of tools that could be used to open up new study paradigms in basic neuroscience. And so you think about those frontier directions. I think that there are opportunities to go beyond electrical interfaces, as I'll describe in my presentation, optical manipulations and recordings of neural activity, but also chemical, maybe microfluidic systems that can be used to do triggered, targeted delivery of pharmacological agents to modulate neural activity. There are lots of efforts these days in thermal and mechanical ultrasound-based approaches. Very exciting. We're not active in that area, but a lot of great work is being done in that space. But you can think about modulation, but also sensing, and ultimately combining modulation and sensing for closed-loop control. And that sensing could occur in the biochemical domain, maybe biopotential, but also biophysical, sort of monitoring in organ function, and then using that information to control organ through neuromodulation. And then from the standpoint of the engineering frameworks that would be used for pursuing those new avenues in modulation and sensing, you think about ultra-miniaturized designs as sort of an obvious direction for development, soft stretchable mechanics to avoid, mechanical damage that could occur due to the interfaces established to soft, fragile neural tissues, complex architectures going beyond point contact locations in the depths of tissues or across the surfaces to full volumetric levels of integration in 3D open sort of network type geometries. We think that's an interesting direction to pursue. Wireless, obviously power, data transmission kind of paired with miniaturized designs makes a lot of sense. Closed loop control, as I mentioned before. And then in certain cases, you would like your neural interface technology to operate for just a finite period to address sort of a temporary patient condition. And in those sorts of contexts, you'd like to be able to build your devices out of materials that would bioresorb, just melt away harmlessly in the body after the devices are no longer needed. So that's kind of the overview. Then the question is, how do you begin to pursue those directions, and what kinds of materials would be attractive? And we feel like semiconductor nano materials, nano membranes, nano ribbons in particular are attractive as the sort of functional basis for those kinds of devices, providing the semiconductor functionality for the electronics, the optoelectronics as well, because making materials very thin leads to high degrees of bendability and relatively straightforward routes to heterogeneous integration with polymeric materials. So blending hard and soft materials together in strategic layouts is a engineering direction that we've found to be useful in this broader context. And then from the standpoint of material scientists, you might ask, well, how are you going to create those semiconductor nanomaterials out of sort of device grade materials? And you want to think about, the mainstays of conventional electronics in terms of the materials themselves, silicon, compound semiconductors like gallium arsenide, gallium nitride, and so on. And there are a variety of ways to do that. And we've sort of exploited top-down strategies that allow us to sort of build on more conventional planar growth techniques. And this is an example of multi-layer epitaxial liftoff, where we grow using MOCVD, alternating stacks of aluminum arsenide, gallium arsenide, etched down through that multi-layer stack, immerse it in an etchant like hydrofluoric acid, which will eliminate the aluminum arsenide at a rate of about 1,000,000 times faster than the gallium arsenide, thereby allowing you to lift off bulk quantities of semiconductor materials lithographically defined device level quality for ultimate assembly into functional devices by hybrid integration with polymeric materials, as illustrated here. A sheet of PET, for example, serving as a substrate. And what we've done is we've created materials using that multi-layer epitaxial liftoff approach, and then soft stamping techniques to manipulate those materials, spread them out in a deterministic way onto a foreign substrate, in this case PET, to yield a flexible type of device that allows for mechanically compatible integration with soft neural tissues. So that turns out to be a straightforward path. You can develop very high performance, flexible, and even stretchable electronics using those types of concepts. It turns out, though, for implantable devices, one of the biggest challenges is in keeping biofluids away from the active electronic components. That is, developing encapsulation materials that can really serve as exceptional barriers to biofluid penetration. And there you can use similar types of liftoff techniques, not now for the functional active materials, the semiconductor materials, but now for the encapsulation layers. And here we've used silicon carbide. It's biocompatible material, can be grown at a wafer scale, can be lifted off of the underlying growth wafer, and then transferred onto the target substrate to serve as that barrier function. So you put all that together, you can begin to build systems that provide unique capabilities as neural interfaces. And this was sort of a high water point for our work along this direction. It's an array of more than 1,000 independent sensing and stimulation nodes. Each one of those nodes includes a pair of silicon nanomembrane-based transistors, one of which is serving as a switch for multiplexed addressing, which turns out to be very important as you scale toward high density, high channel count systems. The other transistor acts as an amplifier, local amplifier, to improve the signal fidelity. And in this case, we've used a transferred layer of thermally grown silicon dioxide as that barrier layer, as the encapsulation structure on top of this system, allowing for long-term stable use in a biofluid environment. And this is some work that we did with Bijan Prasad to demonstrate that technology in a non-human primate, placed on the visual cortex and then presented with visual cues for mapping at very high spatial and temporal resolution the electrical activity associated with response to that visual cue to demonstrate kind of the capabilities of the devices. And so then you would ask, well, is that really a scalable approach or is it an academic curiosity? And I think for any electronic system to be truly scalable, at the levels that we're thinking about anyway, millions of measurement sites, for example, I think alignment with foundry level fabrication capabilities is probably pretty important. And so we actually formed a partnership with XFab International. It's a mixed signal foundry fab located in Germany, to produce SOI micro die, essentially very very tiny, very thin pieces of silicon CMOS that we can lift off by eliminating the underlying buried oxide layer, and then manipulate with stamps to spread that kind of functionality out over large areas. And so this was just a demonstrator at a human scale using that kind of approach, transferring these microdive, these very thin pieces of silicon CMOS across a sheet of PET in this case, using stamping approaches to sort of modulate the local density of these sensing nodes to match with anatomical regions of interest, just as a demonstration of what we think is a scalable approach ultimately for an electrical interface in this kind of sort of microelectrocorticography space. It's about 30,000 channels, no animal model studies with this system, but a functional device that has all the right characteristics. So that's where I think we began to sort of shift our attention, or maybe expand our attention, to think about optical interfaces, because I guess it's my belief that that might be an equally fruitful direction for an academic group to pursue, given the tremendous amount of industry and startup activity in high resolution electrical interfaces. So let me say a little bit about that, because this represents a very active area for research in my group currently. And so it's going back to this idea of expanding the range of sensing and modulation from electrical to optical. And what allows for that are genetic modifications that can create optical sensitivity to neural activity and neural modulation. And so these are techniques of optogenetics, and I'm sure everybody is familiar with these sorts of approaches. Is really a powerful complement to electrical stimulation for modulating neural activity, whereby genetic modifications create light-sensitive ion channels that can then be exploited for direct cell type specific excitation or inhibition of neural firing. And this turns out to be a very, very powerful technique, widely adopted now by the neuroscience community, but at least initially, and to a large extent today, deployed with rather primitive engineering approaches, basically external light sources, fiber optic coupling strategies to deliver that light down to the genetically modified region of the brain that is of interest for neuromodulation, fixed to the head using dental cement and a conventional fiber ferrule type structure. And that works pretty well. It does get light into the brain. You can modulate it by control of that external light source, but it has confounding effects on the natural behaviors of the animals that one would like to study using the techniques of optogenetics. There's a physical effect of that tether that modulates behaviors. It also prevents studies of social interactions between pairs of animals, or interacting social groups, because those tethers immediately get tangled up. And so it was our thought that maybe with some engineering expertise, we could offer an attractive alternative to that particular approach for controlling light illumination at deep regions of the brain. And so there we use the same kinds of approaches I already described to you. It's basically growth techniques that allow us to lift off ultra thin layers of active semiconductor materials, in this case, indium gallium nitride for blue emitting LEDs, where we lithographically define the lateral dimensions. The thicknesses are limited just by the thicknesses of the active materials decoupled from the underlying substrate, which allows you to build LEDs that are far smaller than those that are available commercially. So dimensions that are comparable to an individual neuron and below, actually. So, lateral dimensions that might be in the range of 10 microns with a thickness of 1 micron, kind of in that regime. You can lift them off from the source wafer, use these printing techniques, put them on a piece of plastic, in this case in the geometry of a thin, flexible filamentary probe, shown here wrapped through the eye of a sewing needle to give you a sense of the flexibility. And then that allows you to basically deliver the light source directly into the brain region of interest. And if you couple that kind of cellular scale LED technology with a back-end piece of soft electronics for wireless power transfer and wireless control, you can build an entire system that's fully implantable. So the wireless harvesting and control unit sits just superficially under the skin on the top of the skull. The probe passes through a cranial defect down to a deep brain region of interest, and that's kind of the way that it works. And so you can do this with minimal burden on the animal in terms of weight and physical constraint. And we don't really see any kind of alteration in the natural neuromotor behaviors, and it also allows for this sort of neuroscience of social interactions to be studied by elimination of that physical tether. The other thing it allows you to do is to think about optogenetic studies in other parts of the nervous system. So the peripheral nerves, for example, the sciatic nerve is illustrated there on the left. These are just soft, flexible, tiny LEDs without the need for batteries. So you can really place the light emitting functionality anywhere across the body of the animal. So this is a peripheral nerve, and in this case on the right, shown interfaced with the spinal cord. And as I mentioned before, we do careful measurements of locomotor behaviors of these animals after implantation. And this is an example of a mouse on a running wheel with a green emitting LED, wirelessly powered, wirelessly controlled, using the design features I just described to you, interfaced with the sciatic nerve in that soft muscle location. We are unable to measure any significant effect on the natural locomotor behaviors. And then, as I mentioned before, now you can study interactions between colonies of mice, each one individually and separately controlled using wirelessly powered, wirelessly controlled LEDs. And this opens up some pretty interesting opportunities from the standpoint of neuroscience research, thinking about the neuroscience of the individual brain, but maybe even more importantly, I think long term, understanding how the brain operates in the context of social interactions. And so we published another number of papers in that general space with neuroscience collaborators. But again, we're engineers and we're trying to develop tools and then make those tools available. So we don't want to get in the behavior of just publishing sort of hero technology results in journals and then moving on. We would like to be able to follow through and provide access to that technology to, anyone in the neuroscience community who might see value in it. And so for that reason, we set up sort of a lifestyle-oriented company. It's not designed for an exit strategy or for making lots of money. We just use it as a vehicle to provide access to the technology. It's this company called NeuroWorks, and they've done about 350 systems, as illustrated in the slide, and about 25,000 of these implants, single-use implants, about $20-$30 a piece. So, fairly cost effective for these kinds of studies, and those are deployed worldwide. So doing what we can to sort of take the next step. Translation not in the context, obviously, of human use, but nevertheless trying to contribute to the community beyond just publishing papers. So what's next? You can think about, those multiplexed sheets, those microelectrocorticography systems I described previously, but now in the context of light emitting displays and exploiting, not electrical interfaces, but optical interfaces enabled by the techniques of optogenetics. So here's an example of a device we published earlier this year. It's basically an optoelectronic display. It's an array of these cellular scale LEDs designed to mount on the surface of the brain, on the cortical surface, emitting at tissue penetrating wavelengths. So we have red sensitivity in the optogenetically produced optically active ion channels. And now we can, in a spatiotemporally controlled manner, manipulate brain activity in this way. The electronics get a little bit more complex, and so they're a little bit larger than what's sort of available in terms of real estate on the surface of the skull. And so we move the electronics onto the back, and then we connect the electronics to the display with these stretchable sort of serpentine type interconnects, but still battery free, minimal mass load on the animal, and flexible and compliant to allow natural movements and behaviors. So that's an example. And we also published with that technology studies of animal models and learning behaviors. So we actually program in learning behaviors through spatiotemporal control of that optoelectronic display system. And I won't get into the details. There are a lot of sort of biological results, animal model results, and you can take a look at that paper to understand the findings associated with this technology. So what's next? We're very interested in social interaction. This is unpublished results. So this is I think maybe, well, by far the most sophisticated sort of battery-free wireless implant that we've developed for small animal models. So you can see here we have 3 channels of EMG for monitoring behavior of the gut. We have 2 channels of EEG for monitoring the brain. We have 2 platforms for optogenetic control independently of the gut and the brain. And then we have devices that allow us to measure a broad range of physiological signatures associated with natural behaviors. So heart rate variability, respiration rate variability, physical activity, and orientation. And in this case, we have large sort of naturalistic environments in which the animals can engage and interact with one another. And in this particular case, we have 11 animals, all of which have this kind of control system implanted into them. And we can independently address each of the animals simultaneously. And so we have a manuscript and submission around that technology and a variety of findings in gut-brain axis studies enabled by that sort of platform. So let me transition to the last topic, just kind of going quickly here to give you sort of an overview. Happy to answer questions. If you have any, just send me an email and I'll follow up with you and try to answer any questions you might have. But let me move to this last topic that I wanted to discuss in this presentation. And that is in the notion of 3-dimensional interfaces to neural systems. So you can think about these filaments and meshes as having utility for engagement across surfaces or, as I mentioned before, at point contact locations in the depths of neural tissues. But what would it take to sort of distribute that kind of functionality sort of across a volumetric space? And how do you do 3D sort of open framework electronics and optoelectronics? How do you achieve that in the first place? And the question is really fairly simple to pose, and it turned out to be simple to address as well, luckily. And the ideal would be a strategy that would allow you to take the most sophisticated planar electronic and optoelectronic technologies and somehow configure that system as a final step to move spontaneously up out of the plane of the originally constructed microsystem and move into sort of 3-dimensional space and kind of that open network type style, maybe with a geometry roughly reminiscent of a neural network or a vascular tree, for example. And you like to be able to do that in a way that doesn't impact at all the front end fabrication steps and the kind of materials that support the most sophisticated forms of electronics, CMOS electronics is illustrated here, optoelectronic devices as well. So the question is like, how do you do that? And it turns out to be pretty simple. Here's an example. And what you do really builds on some of the ideas I presented at the beginning of this talk, this notion of growing thin film materials on an underlying supporting substrate and then undercut etching and lifting off those thin sheets. And it could be just the material itself, or it could be a fully functional integrated circuit, as I illustrated through that collaboration that we had with XFAB International using an SOI platform. So let's assume that you've done that, and you've done that not only in the form of a uniform sheet, but you also lithographically pattern that sheet into, in this particular example, a filamentary serpentine mesh type architecture. So it's still in a 2-dimensional layout. You lift it off of the source wafer, and then you bond it at selective sites to an underlying biaxially stretched elastomer substrate. And then if you relax that stretch, you relax that pre-strain, what it does is it imposes compressive forces on that planar filamentary serpentine structure at those bonding locations. And the consequence of that is at the unbonded positions, you get spontaneous delamination from that underlying elastomer and a consequent coordination of translational and rotational motions that achieves a 2D to 3D geometry transformation. And so in a deterministic way that can be modeled. So this is finite element modeling through the collaboration we have with Professor Yonggang Huang's group, just showing that process of 2D to 3D using that controlled buckling scheme. And you can do that essentially with any kind of planar material. This is an example published some years ago now, where we've done that in device grade monocrystalline silicon, just to show you how that works. This is cross-sectional view, so you can begin to build 3-dimensional structures. Now, there are 2 ways you can go. You can think about that as maybe a starting point for active electronic kind of skeletal structure around which you could grow neural tissue, and we're doing that. I won't describe that in this presentation, but that works. And so you basically embed electronic functionality throughout a 3-dimensional neural tissue, allowing for, two-way communication between the biotic and abiotic systems, kind of with an attempt to blur the distinction between technology and biology. The other thing you can do is you can think about those three-dimensional frameworks as a way to engage with organoids, which is a very hot area in neuroscience research and biological research more generally. And I'm sure most of those listening to this presentation are already familiar with this kind of technology, but just to review it quickly, you take cells from a human subject, you differentiate them into different cell types, and then in an in vitro setting, you allow those cells to grow into small scale versions, in a sense, of organs that are naturally occurring in the human body. So there could be neural, intestinal, hepatic. They're three-dimensional in nature, and so they don't interface very naturally with two-dimensional multi-electrode arrays, for example. And so you really need a three-dimensional system to allow for that kind of engagement across the surface of a three-dimensional organoid, where the diameter of the organoid might be in the range of a half a millimeter or millimeter. So the question is, how do you do that? You use these buckling techniques I just described to you, and through detailed engineering of the mechanics, the diffusive characteristics, the geometries, it turns out that you can wrap around one of these tiny spherical organoid structures high performance electronics for electrophysiological monitoring and stimulation as well. And this is kind of the most advanced version that we published just this year. You can take a look at the details there, but it provides a capacity to interface with the outside surface of the organoid, hundreds of individual electrode sites that can be addressed using external electronics. And all of this is guided by quantitative modeling of the mechanics, again, through collaboration with Yonggang Huang's group, not only at the level of the interface to the organoid itself, but to the external electronics as well. So we can understand at a system level how the mechanics sort of play out. So we can do a lot of optimization just based on modeling. And then once we've optimized, we go into the lab and we can fabricate these things. There's a CT image of the structure on the right. So we encompass about 95% or so of the surface of the organoid. And this is an example of 240 channels. We're not only monitoring the electrical activity, but we're stimulating at different sites and then looking at the connectivity of the network by monitoring electrical firing behavior at all of the other sites. And so it turns out to be sort of a useful platform, extending sort of the capabilities in electrophysiology that exist, using standard planar systems as applied to organoids. And this is some unpublished work. I'll just conclude with this, where we can use these frameworks to study not only individual networks, we use them as mechanical fixtures, in a sense, to hold pairs of organoids relative to one another. So we can do deterministic formation of assembloids, and not only form the assembloids, but monitor them and manipulate their electrical activity. So here's an example of a cortical and spinal assembloid formed with these structures, and we can monitor the electrical firing activity in each one of those organoids, and we can watch when the firing activity starts to become synchronized, which corresponds to the formation of a neurite bridge in between them. And then we can come in and we can simulate spinal cord injury. So we work with a rehabilitation hospital to understand the mechanisms associated with injury and recovery from the injury by injuring the spinal organoid and watching behavior in the cortical organoid that results from that. So this is a final example. We're doing neuromuscular junction formation. So here we're combining a neural organoid with a muscle ring. It's a little bit different geometry in the 3D structure, but allows us to understand the electrical junctions that form between a neural organoid and a muscle organoid. And this is also unpublished, but just to give you a sense of where this is going and sort of the engineering versatility of some of these 3D assembly techniques that we've been working on. So with that, I think I'm out of time, maybe 1 minute over. I apologize for that, but hopefully this has been of interest for an engineer's role in this broader area of neural interface development. And I shared with you some of the latest work and unpublished work in these optogenetic displays and these 3D mesoscale frameworks. It's all very collaborative. I've mentioned Yonggang Huang a few times, a few other collaborators in engineering science, but the connection to clinical medicine and neuroscience research is very important guiding force in prioritizing our efforts in the engineering aspects of what we're doing. But the students are the most important people. The collaborators are great, but the students are the ones who do the work. So I just want to conclude by acknowledging them for their incredible efforts and their creative ideas, and thanking you again for the invitation to participate in this event.
Amazing talk, John. Thank you very much. Exceptional work and very well presented as always. Let's now move on to the second part of this event where we will hear 4 short talks. My job is to introduce the first 2. First will be Sam Kamali, who is the CEO and co-founder of MyoNerve. This is a Cambridge-based medtech startup that is developing a wearable neurostimulation technology for stroke and brain injury rehabilitation. He will talk about a wearable neurostimulator that uses a patient's own EMG muscle signals to trigger functional electrical stimulation, moving fingers and hands of a paralyzed limb in real time. Then we will hear from Ali Williams. She is a Medical Research Council-funded PhD researcher in the Cognitive Neuroscience unit of the MRC Cognition and Brain Sciences unit in the University of Cambridge. And she's also a Cambridge NeuroWorks Frontier Fellow. She will talk about how principles from motor learning and neuroscience can help reshape rehabilitation through wearable technology. So Sam, the floor is yours.
George, thank you very much for the introduction. I'll just share my screen now. And we'll just ask if you can see that, just so I can get started.
Yep.
Great. Well, hi everyone. It's a pleasure to meet you all today. I'm here today to talk to you about MyoNerve, which is a closed-loop neurostimulator to remotely monitor and treat stroke-induced paralysis. Now, my journey into neurotechnology started when I was just 11 years old, after my cousin, pictured here, suffered a stroke on the playground at school that changed both of our lives. He ended up in a care home, and I ended up studying neuroscience at university, and I would bring back what I learned from my lectures to his home in a bid to help him with his rehabilitation. And this was the first time in this picture that he was able to catch a ball for the first time in 10 years. Now, at university, I met Professor Riley Green, who became my supervisor, and together we developed these biomaterials to interface with the nervous system and create medical devices to treat neurological diseases such as stroke and paralysis. There I met my co-founder, George, who's a PhD candidate, developing these miniature circuit boards that he's actually implanted into the brains of primates to record local field potentials during concurrent deep brain stimulation, and using hardware to filter out the stimulation artifacts. So together we created this little team, and with our commercial advisors, we realized that my cousin isn't the only one. He's actually one of 8 million stroke patients who suffer from upper limb paralysis every year worldwide, 11% of whom live in these 3 regions: the US, the DAC, which are the German-speaking countries of Europe, and the UK. Now, although 11% live in these 3 regions, they actually contribute towards 55% of the global stroke rehabilitation market size. That just goes to show how much we're willing to spend on stroke rehabilitation. One of the devices that we spend our money on are electrical stimulators, which are the most promising form of treatment for patients. But ironically, they're handheld with these long wires and sticky electrodes. Patients and physiotherapists are not encouraged enough to use them because it's just a nuisance to use. To add insult to injury, 60% of patients miss their 6-month assessments because clinics are too far, and 75% of patients give up on their rehabilitation goals altogether because of just the lack of physiotherapists. That's why we said a stroke device must have a high density array of reusable polymer-based electrodes embedded into a wearable band that you can then wrap around your arm to provide a 60% increase in functional strength after just 2 weeks of use. That's thanks to our P-dot-based polymer electrodes having a near 100% classification accuracy of the muscle fibers in the arm to then provide targeted electrical stimulation that can move the fingers of the hand in real time. Now, what's especially powerful is we want to pair devices together so that for patients who are severely paralyzed and there is no EMG muscle signal to leverage on to target the electrical stimulation, we put a MyoNerve on a physiotherapist and we map their EMG and their hand movements and mirror that into a patient's hand remotely. And this sort of platform means that a physio and a patient don't even need to be in the same room as each other anymore, enabling remote monitoring and scaling telerehabilitation across regions. We've built our first proof of concept device, and we were able to remotely control the fingers of the user from Athens, which is 1,500 miles away from us in Cambridge, in real time. That's just proving the concept of virtual wards and remote physiotherapy, enabling therapists to be active participants in a patient's therapy for the first time. Enabling physios to be active participants in a patient's physiotherapy for the first time ever. And we've publicly demonstrated this device, and this is now, in fact, an outdated version. We're working on these new ones, and we'll be more than happy to share with you these once they become tested and available for public demonstration. Now, we want to leverage on a US business model. We've already mapped, the US reimbursement codes and how much we want to sell the devices for. And we've even designed these new workflows for physiotherapists in virtual wards where they can now have 3 patients at a time in group therapy in 1 hour, essentially increasing the amount of patients they're able to see per day and actually increasing the profits they're able to generate as well. Via this model, we're able to generate 8 times the profits versus traditional one-to-one physiotherapy, whilst also being far more, generating a lot more confidence in the quality of the care that clinicians are able to provide, and also the output as well, which we're estimating is a 60% increase in strength after 2 weeks. We're not the only electrical stimulator out there. There's Cala, which recently raised $50 million. They're, I think, a spin out from Stanford. You've got some other devices in Europe like MindMaze, some purely remote patient monitoring devices, but MyoNerve is the world's first electrical stimulator with remote patient monitoring that's enabled through EMG triggered an EMG triggered setup with polymer electrodes, allowing for active telerehab at a fraction of the price. Now we're increasing our global presence. We've raised £330,000 over the past 12 months, including $150,000 from Northwestern Memorial Healthcare. So it's a pleasure to meet Jonathan ROGERS here virtually, and I hope to see him actually in a few months' time once we get invited out to Chicago. So I'm using this opportunity to also introduce myself, but I hope to see you out there soon, John. We've also raised £100,000 recently last week from Innovate UK for the hospital to community themed grant, which is where MyoNerve's sweet spot is, because we're trying to take the hospital care out into the community with our virtual care setup. Over the past 12 months, we've hit all of our milestones of our Cambridge NeuroWorks project, all the way up to our first in-human trials. And now we are working on our flexible alpha device with Northwestern Memorial Healthcare. And we're trying to get out into the Shirley Ryan Ability Lab, which is arguably the #1 hospital in the world for neurorehabilitation, after which we'll grow our clinical evidence on patients and work towards a pivotal trial. And this is all towards a, $80 million 7-year revenue. And again, just referencing some of our competitors who've generated just $40 million in revenue in devices alone, excluding the software as a service. And we're raising right now £1 million to work on our regulatory pathway to increase the manufacturability of our electrodes. We can create some devices, put them into trials, and work continually on our commercial case in the US. If you have any questions or you'd like to participate in any shape or form, whether it's providing some engineering help, connecting us with clinicians, or even participating in the round, please do reach out. I'm more than happy to share more. Thank you.
Thank you very much, Sam. Let us move now to Ali.
Hello, let me share my screen. Hopefully everyone can see, but hello, I'm Ali. I'm here to tell you about my NeuroWorks project, which we are calling Mika. My team and I are building the first non-invasive wearable that measures pelvic floor engagement and provides real-time biofeedback to train the brain in order to build awareness and control of deep muscles, specifically of the pelvic floor. I'm working with my two co-founders in Tamar Makin's neuroscience lab, the plasticity lab. But as you heard earlier, I'm actually Tamar's yoga teacher, and that is how we met and how we decided to work together. We became fascinated by a simple neuroscience question, which is how do we learn to control muscles that we can't see or feel? So deep muscles are muscles that don't have as much feedback. For her, it was her shoulder after a shoulder injury. And we decided to build a technology to address this question together. From the beginning, the pelvic floor was our holy grail because it is structurally critical, but also because there is an enormous unmet demand. And this ranges from urinary incontinence at one end, and that impacts 14 million people in the UK alone. In our first study with postpartum women, we recruited for healthy postpartum women, and half of them actually ended up experiencing urinary incontinence, which I was shocked by. But beyond that, pelvic health is also tied to conditions across gender and across lifespan, including back pain and sexual dysfunction, and likelihood of experiencing one of these conditions also increases with age. There is a solution, which is physiotherapy, but this is limited by cost and by access. And importantly, for it to be effective, it has to be done correctly. There is a market to address this problem, this gap, but generally solutions fall into two main categories. They're either invasive, and this can be uncomfortable, or it's not, there are a lot of reasons it might not be ideal. It's not so difficult with movement. And then there are reminder apps like Squeezy, which the NHS recommends. And while these are useful, they don't teach you how to engage, and they don't track if you're actually engaging correctly. So they assume a level of knowledge and awareness that might be lacking from the outset. Our solution is the first non-invasive wearable device, which uses machine learning and AI to deliver real-time vibration to the hip bones to help users to build awareness and control of their pelvic floor. We're naming it Miss Smarty Pants, and it delivers personalized real-time feedback to train proportional voluntary control across functional movements, helping the brain to build proprioceptive awareness of the pelvic floor. It also works. We've tested it extensively across healthy women and postpartum women, and also against men, and it's been validated against the gold standard vaginal probes. And we're currently conducting our first longitudinal study to demonstrate that users improve over time. While the pelvic floor device market does have many existing solutions, Miss Smarty Pants is the only solution addressing pelvic health as a neuromuscular problem. And it's the only non-invasive solution for real-world pelvic floor training. Alongside that, we know that there's strong demand. We've conducted a lot of interviews with clinicians and had a lot of discussion with our users, and it showed exceptionally strong demand. And so we're building our device into a platform for B2B clinical and expert pelvic health trainer use connected to online training for users. To bring this to market, we'll begin with clinicians and professionals before bringing our solution to some of the 700,000 women in the UK who give birth each year. Eventually, we'll scale to other user groups. Our patent was filed in January with Cambridge Enterprise, and it covers all deep muscles. So this also gives us potential to scale for performance and additional rehabilitation needs. For example, by white labeling our technology. But the principle is for deep muscles that don't receive feedback or where we are unaware of what we're doing, helping people to learn the proprioception to be able to access them through day-to-day movement. Over the next 12 months, please ignore the dates on this. I can't believe that we're a year ahead. It should be 2026 to 2027. We're going to begin our co-design program, working with specialists and move from proof of concept, which, as I mentioned, we've tested on over 200 people, to a working prototype. And we're supported by Cambridge NeuroWorks and by grant funding to do this. We're also preparing regulatory pathways, and we'll be spinning out to raise money at the end of the NeuroWorks program. But for now, we are focused on moving from our strong foundation to next steps. And it is such a privilege to be part of Cambridge NeuroWorks. I've been so inspired by the other fellows, past and present, and by the team. And I'm excited to keep driving this project forward. Please get in touch if you're interested. If you are know people who are in pelvic health or rehabilitation, and if you'd like to chat, I'd love to hear from you. Thank you.
Thank you very much, Ali. Very interesting work. Now I'd like to introduce two more presenters from PolyU. First of all is Professor Liang Hualou, who is a chair professor, excuse me, who is a chair professor of neuroscience and artificial intelligence in the Department of Language Sciences and Technology. At the PolyU pair, he is also a member of Research Institute for Smart Aging. Professor Liang's research focuses on neural data science, machine learning, and biomedical natural language processing. His work advances the use of spoken language technologies and AI for healthcare applications, including dementia prediction. The second speaker from PolyU is Professor Vivian Hui, who is an assistant professor at the School of Nursing. At the PolyU pair, she is a member of the Mental Health Research Center. Excuse me. So Professor Hui's research focuses on applying AI, natural language processing, large language models, and health informatics to improve patient care and health outcomes. This includes understanding patients' needs, supporting cancer survivorship, and domestic violence research, and enhancing healthcare delivery. Now, Professor Liang, the floor is yours.
All right, and hello everyone, and thank you, Professor Chen, for your kind introduction. It's an absolute pleasure to be here. And this is Hualou Liang. Actually, I recently joined PolyU less than 6 months, and after I've been in the US for about 30 years. My research has been in computational cognitive neuroscience, and more recently, I work on the AI in digital health. That's the topic I'm going to share with you today. And to start with, and we published a short paper a few years back, actually right before ChatGPT released publicly. And actually, we are the very first one to report using the large language model, particularly GPT-3, for early prediction of dementia. So when the work just published and immediately attract a large media attention, and such as like Recorded Today, Jerusalem Post, New York Times, and Tribune Spectrum. We even have a short entry in the Wikipedia page for the GPT-3. And so when the paper just published, and the OpenAI present co-founder Greg Brockman immediately tweeted the work, saying this is interesting first result of using a GPT embedding for the early prediction of dementia. So that's how we hook up with OpenAI. We established a collaboration until today. And the goal for this project is to try to develop AI-powered, speech-based platform that is cost-effective and user-friendly for early detection of dementia. And we know the problem of dementia affects over 55 million people globally. A number projects to surge to more than 100 million by 2050, but there's no cure for the AD. Conventional method for early detection, including neuropsychological testing, clinic evaluation, fluid biomarker, and a medical image, they are all expensive, time-consuming, and impractical for scaling screening. Therefore, there's unmet need to have a method for early detection of dementia. So the idea is really simple, what I'm going to tell you. And so once you have the voice recording, we do a simple transcription. We call it speech-to-text transcription. Once you have the transcription, you feed into the large language model, you get the text representation of the transcription. This process, we call it text embedding. And once you have a string of a magic number and the text representation of your input, then we simply feed into the general downstream task, a regular machine learning model. We can do classification or the regression in machine learning term, or simply we say, hey, we just do the classification, whether it's AD or not AD, or we do prediction. Basically, we try to predict your cognitive score of the subject, which is called regression in machine learning. So the core idea here is simply the text embedding, which I'm going to show you in my next slide. So what is embedding? How does it perform? So the idea is really simple. For example, when you have an input text, let's say PolyU pair, you feed into a large language model, then your output is a string of a floating number. So this is quite different to nowadays most people using large language models such as the OpenAI ChatGPT. Basically, you have the input, you ask whatever question you have, you get output here. We also have input and output, but what we get here is just a string of the number. Once we have this number, we simply fit into the conventional machine learning model to do the classification and regression. Turn out we tested this model on more than 237 subjects. We have 166 for training and 71 for testing. And of course, we just follow the standard, like time for the cross-validation for the training and testing. And turn out the result pretty amazing, which I'm showing the one slide, one plot, one figure showing here. We call it ROC curve. Basically, the top two curves provided by the large language model perform quite well compared to the traditional method. That's the middle curve. But if you have the model performance somewhere lying in the middle, this diagonal term, 45-degree line, that you didn't do well, pretty much like a 55-50. But we are here right over the corner. And so in the find of sanity check, we send our algorithm to an international competition for dementia prediction happened 2 years ago, called the InterSpeech 2024 challenge. And they have two tasks. One called MCI, mild cognitive impairment detection. Another task called MMSE is kind of a cognitive score prediction. And it turned out our algorithm did quite well, and we ranked #1 for the MCI detection. And now, I'm sorry, this is #2 for MCI detection and #1 for the cognitive score prediction. And I think let me stop here, and I'll give my floor to the next speaker. Thank you.
Thank you very much, Professor Liang. Professor Hui, your floor is yours.
All right, is everyone able to see the screen?
Yes, very well.
Okay, thank you. Thank you everyone. This is Vivian from PolyU School of Nursing. So today I'm going to share a list of applications about LLM in nursing. So I'm trained as a nurse and worked as a clinical nurse for a few years before I pursued a PhD at the University of Pittsburgh. And once I came back to Hong Kong Polytechnic, I work on using AI and also LLM to nursing education, on clinical practice, and also exploring online health communities with LLM. So the first application that we decided is actually for the students. So technically, most of our curriculum for the nurses, they mainly focus on the clinical skills, how to do the wound dressing, how to do the Foley insertions. But rarely there is a system to teach the students how to talk with the patients or how to pitch an idea to the senior managers with the current trend of AI. So we figure out the current education problem in clinical education is the limited opportunity for the nurses to pitch ideas to someone who are not in the healthcare field. So we decided a pitching script analysis tool based on our previous homework and also some expert feedback from the pitcher, from the healthcare and also business experts. And then we provide automated feedback for the students, how to improve their pitch. And then we also provide them the feedback mechanism. So before they come to the teachers for the consultations, they could actually review their pitch and also revise them first. So we compare these models with the analysis, and also we demonstrated the LLM can actually do way better than the teachers because they can summarize their ideas very quickly, and also the students report a positive experience by using the system for some personalized feedback 24 hours. The second one is mainly for the patients who are in neurosurgery. So patients with neurosurgery, probably they are very complicated and have huge concerns about what kinds of side effects, what kinds of precautions before the surgery. So we worked with the QEH hospital in Hong Kong and also the nurses, doctors to collect a bunch of the Q&A pairs to build a RAG system. And then we used a large language model to do a neurosurgery specific chatbot in Cantonese and English. So we validated with a mixed method study. We demonstrated actually the assistance API actually outperformed the ChatGPT in 2025. And we also included some expert ratings whether this neurobot could improve in accuracy, relevance, and completeness. We also did some qualitative insights with the neurosurgeons and also advanced practice nurses. And we demonstrate that the neurobot can actually reduce the workload from the nurses. They can also enhance the patient education and deliver evidence-based responses according to the relevant policies and the guidelines from the nursing care plans. The third one is because most of our patients right now, they text a lot on the online social medias, but they don't have enough time for their clinicians, or they don't have enough time to talk to the doctors. So they most likely, they will share their concerns in the Twitters or in the Reddit. So we use the large language models to collect a bunch of narratives from the online health communities on cancer-specific patients. And then we try to extract the information, emotional needs about how they handle or how they cope with the cancer. So we deployed the topic GPT to retrieve all those topics. And also we try to use DeepSeek, ChatGPT, and large language models to rank their topic diversity, coherence, and quality. So in this assessment, we actually found that this topic GPT can also maintain a high topic diversity across languages. And we find out that people with cancer, they share a lot of concerns about the fear of cancer recurrence, about their psychological distress. And also we find out some cancer populations, they share most likely about sexual health concerns, which are very embarrassing. And these topics are very, very hard to get from the electronic health records, because electronic health records is mainly from the clinicians, from the top-down approach, but the online health community is from the bottom-up approach. So that's why we could deploy large language models and collect a bunch of hidden information needs and also the emotional needs from the patients. The current work we're working on is from the mental health, especially for the traumatic patients. The left-hand side is a chatbot developed for their domestic violence. The main problem for these people is actually they rarely seek help in person, and they rely on their offline help-seeking channels such as chatbot. And currently, most of the commercial chatbot, they don't have locally validated information, and they couldn't encourage their high-risk population to seek for the in-person help. So we tried to deploy the help-seeking barriers into the REC system so that the chatbot could be able to find out the red flags and also the signs and symptoms, what are their safety among their conversation, and also try to connect them back to the community with the NGOs or with the nurses in our team, so that we can bring those hidden patients to our community. The second one for EmoBot is also working on mental health. We tried to develop the EmoBot with their counseling narratives and also the WhatsApp counseling transcripts from our NGOs social workers. And then we deployed it, we embedded the WhatsApp conversation into our models. So the language is much more local in Cantonese. And then we also trying to seek for the validation from the experts right now. So these two works are currently in progress. So I hope this sharing is very and can give you some ideas about what kinds of LLM could enhance the nurses and also could enhance the nursing care. However, this is no longer about whether LLM belongs to healthcare, but actually more importantly is how quickly we can responsibly integrate LLM and also validate a better one to make it ethically safe across different touch points of the patient journey. Thank you.
Wonderful. Thank you very much to all four presenters for their very interesting talks. This is great. We will now move on to questions and answers. So we're ready to take your questions, and we will moderate from our end.
All right, this is Wei Xiongzhang from PolyU pair. First of all, I'd like to thank five speakers for wonderful presentations. These five presentations really touches upon two very active research frontiers now. One is a brain electronic interface or human machine interface. The other one is large language models, so-called, the modern AI. So let me get to a few questions now. Before the session start, we already collected some questions from the registered people. Let me get to first question. This is towards Professor Rogers. Professor Rogers, are you there? Okay, you're there. Okay, so another fascinating talk. The battery-free device are beautiful pieces of engineering. The ability to acquire EMG, EEG, and other physiological measurements during natural behavior is genuinely impressive. A question I would like to raise is whether the field sometimes conflates control with understanding. Optogenetics allow us to switch particular neuronal populations on and off, which is normally powerful, but because the stimulation we impose is not necessarily the same as the physiological signaling that occur within the functional circuit, is it always justified to infer normal circuit mechanism from these experiments? I'm asking because the assumption that cell-specific manipulation automatically reveals circuit function now seems quite widespread across neuroscience. Do you think the evidence genuinely supports that conclusion? And what does that mean for clinical translation in human?
Wow, that's a very deep question. Yeah. A whole essay. Clearly, someone who's thought very deeply about these topics. Um, I don't know if I have a good, simple, crisp answer to this very profound question. But I think from a engineering enablement standpoint, you would like to be able to control and monitor. And I think you'd like to be able to do that not only from the standpoint of the neural tissue, the brain and the peripheral nerves, the spinal cord, but you'd also like to be able to monitor the end organ function as well, you know. And so I think by combining all three of those capabilities, that one at least has a hope for teasing out a fundamental understanding. So maybe if the question um, is whether, you know, just neural control and monitoring is sufficient, I would say probably not. You also need to monitor organ function as well. And so I guess that's what we're trying to do in this you know, kind of latest unpublished work that I mentioned, where we're doing optogenetic control of the brain and the gut, but we're monitoring the response of the brain and the gut to that stimulation, and also downstream looking at the overall impacts on other physiological characteristics. So I guess maybe try to answer this question. What we're trying to do is throw as much engineering as possible at the problem, appreciating, I think, the inference in the question that neural control is not enough. And I guess I would agree with that, you know, and we're trying as engineers, you know, we're not neuroscientists. I don't pretend to be one, but we work with them, some of the top neuroscience scientists in the field. And so that's the direction that we're taking. Hopefully that kind of answers your question. It's not a resolution to that issue, but a set of engineering capabilities that maybe allow us to head in that direction in a more effective manner.
Okay, thank you. I have two questions that are related. Let me ask them together. This is also towards Professor Rogers. Is there any solution for helping the patients of dementia with bioelectronics, as this type of patient is increasing every day? Okay. Another, it's you know, almost the same one. What is progress of applying bioelectronic systems as a neural interface in the treatment of neurodegenerative disorders? Please let us know some successful examples.
Yeah, those are tough questions. I mean, you know, along those same lines, people will ask about, you know, treatments for depression, other kinds of, you know, mental, you know, challenges, and brain disorders. I think all of these things require a fundamental understanding of what's going on at the biological level before, you know, an engineering solution could be, you know, targeted. Yeah, I think ultimately maybe related to this question is that in the near term, I think electrical interfaces will continue to dominate. But if you want the kind of precision and control and the ability to really, you know, engage with large volumes of neural tissue, my bias is a little bit more toward optical interfaces because of the versatility, you know, in engineering capacities around imaging, wavelength control, polarization, intensity. There's just a lot more knobs that one can turn with optical interfaces. The big question is when and if the techniques of optogenetics and related genetic modifications for fluorescence detection of neural activity will be approved for human use. And I'm optimistic that will happen. There are some papers where optogenetics techniques are being used to restore vision. And I think that's a first and sort of natural, you know, initial approval. But more generally, I think if those techniques can you know, be more widely adopted and applied to humans, then you know, the kind of control and the precision may allow ultimately for treatment of some of these very debilitating disorders that were mentioned. So I think there needs to be, you know, advances in brain interface technologies and neural control, but also underlying all of that, you know, it's going to require a deeper understanding than we currently have around the biological nature of these disorders, some of which may be irreversible, you know, and may not be amenable to, you know, an engineering or a, you know, pharmacological treatment approach.
Okay, thank you. More or less, we are all kind of on the engineering side. So we approach these medical problems from engineering perspective. Most of the time, we may not, you know, go deeply down to the mechanism, for instance. So here is a good example, like, you know, Professor Lianghua Lou just presented using ChatGPT, that's a large language model to detect Alzheimer's disease dementia. Okay, so just to transform voice or text in, you know, do a compression, come up with the low dimension representation, then do the classification, regression, all those things, and then, you know, do the prediction. So indeed, you know, probably we don't. I don't know. You know, here's a question. Okay, to try to inspire some discussion. So I don't know how much you know what are kind of exact features in the voice or the text that are indicative of dementia. By you know, doing you probably have done a lot of experiments. I don't know if you have analyzed the data. That's one question. Okay, the similar question I can turn around the table, ask Professor Rogers. So you are doing, you know, the kind of a brain stimulation, for example, the electrogenetics. That's, you know, related to the question, the first question asked. So how much do we know the mechanism? Right, you just, you know, turn on the light and off. Why all of a sudden, you know, you can have the effect to control, you know, say a body movement. So overall, what can we learn from your research to help, say, medicine, try to go down to the more deep understanding of disease mechanism, for instance?
Yeah,
this is tended to be a discussion. Okay, please, you know, panelists can jump in and offer your comments and views.
Yeah, I think maybe there are two questions embedded there. I feel like the community has a very good understanding of the mechanisms by which light can inhibit or stimulate neural activity as a consequence of these light-sensitive ion channels that are expressed following genetic modification. So I think that process is fairly well established, and the mechanism by which that genetic modification is introduced typically would use a viral vector that's cell type specific. So that specificity and the delivery mechanisms, I think those aspects are all well understood. I think what remains an exciting open topic is how control of specific targeted neural networks modulates behaviors. And it could be a behavior at the full animal level, or it could be behavior at an individual organ level. For instance, you know, we have used optogenetics to control for overactive bladder activity, animal models. But we know how to do that by optogenetically silencing peripheral nerves that innervate the bladder wall tissue. So, you know, I think in certain instances, the connection is fairly straightforward. That would be a good example. How the brain interfaces to those peripheral nerves and how the control could be established from a brain interface device, that's less well understood. So there are examples in controlling and inducing pain response. You can also achieve that by optogenetic manipulation of peripheral nerves. So I guess what I'm trying to say is neural interfaces at the level of the peripheral nervous system, I think, are a lot easier to understand than those at the brain level. It's just a more complex system, and the nature of interconnections is less well established. But maybe back to the other question, I think the ability to control at least provides a roadmap for how you can begin to tease out neural activity and the consequences on behaviors. And that I think represents a dominating theme for much of neuroscience research these days. And again, I'm not a neuroscientist, but that's what the community seems to be pursuing, that line of investigation.
I would add to that just to say that in motor learning research, for example, for a really long time, research was kind of reductionist in terms of the fact that we were trying to isolate specific factors that influence motor learning, whether that be explicit and implicit or other aspects of it. And the reality is that in the real world, if we're applying this to a human and to human behavior, things don't happen in isolation. So it's important to recognize the limitation of identifying a specific cause and effect or trying to minimize a complex solution down to these components where it is a system. It's more complex than that.
Great. Professor Liang, any thoughts?
Oh, sure. Yeah, I think you asked an excellent question about the feature representation. For the large language model, the embedding, we really don't know what the embedding is, but we just know that a bunch of number. There's some work start working on to figure out exactly what included in the embedding. And we did some work, and it's kind of by trial and error. For example, if I give a sentence, let's say, I love PolyU pair, and what we can do is, we can remove a word by word, then look at the embedding, and based on that embedding, we can determine the model performance, whether increase or decrease. Then we go back to see which word is more important than the other. And overall, they call this kind of contextual representation. And so all I want to tell you is so far it's still not clear. We don't know exactly what the embedding is. And yeah.
I have a question regarding Professor Rogers' work. So it sounds like you focus more on the modulation, say for instance, neuromodulation. That's more on the, my understanding is more towards treatment. But for a lot of disease study, for the patient care, diagnosis is probably as important as the treatment. So because I'm very naive here, I have no knowledge about your work or your field. So I wonder, these nano devices can be used in some way as a sensor, because for diagnosis we need a lot of sensors. And the other thing, go ahead.
No, go ahead.
The other question is, kind of the devices you develop there, that's in order to make use of them, we need to do some surgery, right? So for instance, put into some, open up the skull and, put it underneath. So is there any non-invasive use for your technology in healthcare area?
Yeah, so couple questions there. I guess the first one was around monitoring. So I didn't have time, or already went over by a couple of minutes, apologize for that, but I didn't have time to include any of our work on optical monitoring of neural activity, but we do that as well. I mean, there are also, genetic modification techniques that lead to expression of fluorescent species with fluorescent yields that are modulated by various chemical indicators of neural activity, even voltage responsive indicators now. It's a very active area in neuroscience research, developing these various fluorescent-based methods for monitoring, in general, cellular activity, but neural activity specifically. And so in those cases, we have similar types of probes to the ones that I described for neuromodulation, but in those cases, we have an LED that stimulates the fluorescence and then a equally small and thin photodetector that monitors the intensity of that fluorescence. And so you can do that kind of photometry is what they call it, photometry to monitor activity. And you can also do optogenetic control for closed loop operation. So, we've published on that. There are other sort of, electrochemical sensors. Other groups do great work in that area. We dabble in it a little bit. I wouldn't say we're leaders in that space, but that sort of complements. Again, we're sort of focused on optics. So those are approaches that are very powerful, and we publish a number of papers in that space. In terms of non-invasive, yeah, I mean, we have various skin interface devices for wireless EEG. I think that's not what you're asking. I would say we don't. I mean, they require some level of surgery, and maybe you could say some of those surgeries are minimally invasive, but they're not non-invasive. I think maybe that's a frontier area. If somebody can come up with a good idea of how to get a device in the brain without surgery, that would be pretty interesting. I guess the closest thing that I can think of is a Stentrode technology, not out of my group, but it's a electronic platform delivered in the geometry of a stent, and it's coming up through a peripheral artery. And you get access to the brain through the natural vasculature. And so you're not disturbing the brain tissue in that way. I think it's sort of limited in number of channel counts and where you can place that kind of technology. And then you need, the hardware for control and monitoring. But that's probably the closest thing. The Neuralink has filamentary probes and robotic surgical tools that allow them to insert electrodes into the brain, but in a way that avoids disruption of the natural vasculature. So again, kind of minimally invasive, but still it's a surgery. So I don't know of anything that's purely non-invasive. Somebody else maybe on the panel is aware of something that I don't know of or not thinking of currently.
I mean, one thing to consider is the definition of invasive. Arguably, something that gets placed inside the body, it's non-visible, does not require any intervention for decades, might end up being less invasive to the patient. That's something that attaches on the forehead, is visible, requires a lot of cleaning, daily maintenance. There are human factors to be considered when we discuss invasiveness.
All right, anyone want to add on this? Okay, let me ask one more question. Let me ask something big. So as I mentioned, right, these days, to me, the most active research frontiers include the brain electronic interface, and that's kind of a main topic today. The other area is large language models. And these are very active. So let's try to be next Elon Musk. No, Elon Musk has a Neuralink. He also has a company doing the large language models, right? So how can we combine these two fields in some way? Or put it another way, how can we help each other? People in these two research frontiers to help each other. Say, let me just throw in my thoughts. Can we collect the data using, through the experiments using brain machine interface to feed into, for instance, a large language model, right? Because from there we can collect the brain machine interface. We can collect a lot of data through experiments, using animal, using human. Probably, we can, for instance, if we want to treat a stroke, we can collect the data from animal models, animal studies, and build models, and do transfer learning kind of a style technology to help human. That could be one example. So I don't know. I don't have an answer to going the other way. Large language model. How can we use large language model to help human machine interface? Any thoughts? I want to hear your thoughts.
So may I chip in very quick?
Yeah, please.
Yeah, sure. A couple of weeks ago, I don't know whether the paper already published or not. I read a paper. Basically, they use they call a large language model embedded BCI. They try to use a large language model to interpret the brain activity automatically, and then once try to get some meaningful signal, then use this meaningful signal to feed into this the BCI for the next step. And I think that's just roughly the idea when I read that review paper. And yeah, something I just remember a few keywords like LLM embedded BCI, and it's just a rough idea. I don't remember much detail. Yeah.
Yeah, I think it's a great question. I don't want to dominate the conversation here, but I'll throw in a couple of.
Oh, go ahead. Go ahead. Share your thoughts.
Others. So back to the question of therapeutic uses of stimulation. I should have mentioned that there are techniques for stimulating the brain in a way that can eliminate epileptic seizures. I think George has done some nice work in that space. We had a paper as well where you're using machine learning to identify early signs of the development of a seizure, and then providing either electrical or pharmacological intervention to eliminate the seizure kind of before it happens. And so I think that's a great area for use of these modern AI techniques. There are also stimulation approaches based on interfaces of the vagus nerve that can assist in restoration of function that's been lost from a stroke, for example. There's some papers kind of in that space as well. Of course, deep brain stimulation for Parkinson's. A lot of different examples. But the other area I think where machine learning can be very powerful is just in human machine interface, and I think there Neuralink has done some amazing things in terms of decoding brain signals and translating them into control signals for interfacing with a computer system or a robot or things of that nature. And maybe coming back to Ali's comments there, I think maybe a fundamental understanding is not so essential. You're just trying to translate what's happening in the brain without getting a molecular level understanding of the neural architecture, but you're just sort of empirically using collective brain function monitored with many thousands of channels and converting that into some kind of interpretable signals for controlling machine or a computer interface. So I think there's kind of those two domains of use in therapy and also just in human machine interface.
All right. We're kind of run out of time here. So okay, let me thank the speakers for very inspiring and thought-provoking talks, and also the discussion. Let me, George, throw back to you.
Yeah, nothing more from me, just to thank everyone, especially people from PAIR, for this wonderful alliance that we managed to build. Thank you to the speakers. Amazing talks, just highlighting what the state of the art is today in this field. And thank you all for attending. One reminder that you can get access to this content and more from resources that would be posted along with the talk. I encourage you to join Cambridge NeuroWorks, look at the website, and join the Connect Health Tech app for future updates. There is one more series in this, one more episode in this series to be announced soon.
I also like to thank George for organizing everything. And this is the second seminar in this series. And as you mentioned, we'll have one more. I'd like to thank all the speakers for your wonderful contribution in the seminar, especially to Professor John ROGERS, a true friend of a pair who are giving help in all aspects. So last time you were here to give us help on how to do interdisciplinary research. And today we definitely see this is another type of interdisciplinary. You can see all the speakers from very different fields and contribute to the common problem. So I will also like to thank my colleague Vision in the discussion session. And finally, last not least, I would like to thank all the participants. Nobody you participate through Zoom, through the streaming and whatever method. I think your questions, your participation really make this seminar very impactful. And so thank everyone, and the seminar is adjourned. Thank you.